All right. Thank you for this great opportunity to present our research work, recent research works. So this big project is now being supported by so many collaborators, including postdocs, students, and administrative staffs. So I would like to thank all of them in advance for their great contribution to this super challenging and high-risk research project. So this very first slide shows our vision and the challenges. So our vision is that we would like to build the better society in which no one suffers from the fears of the extreme hydrometeorological disasters by controlling weather social coupled systems based on the democratic social decision making. So what are the challenges? The first, we need mathematical methods to leverage chaos. So we would like to leverage the chaotic nature of the atmosphere, but how? That's the question. The another challenge is we need a meteorological theory or physical understanding of the phenomena to upscale our interventions. So our weather phenomena is a macro scale. This is big, and our human intervention is very small. So how to upscale that small interventions into the macro scale weather phenomena? And lastly, we have to design the acceptable weather control in society. So we recognize our weather technology is a potentially the new social infrastructure. So how to maximize the potential of that social infrastructure installed in our real society. So let's start from, okay, how it goes. Okay, let's start from the mathematics. So this is the basic idea. On the left, this is the intensity forecast of the Hurricane Herbie. So if you look at the very left side, we start from the small differences in the initial condition. However, when the time goes on, our prediction results of the intensity diverged, right? So if you look at that, we can expect that the small change of the initial condition will change significantly in the future. That's the idea of the chaos control. But is this the end of the story? No. As we learned in the previous very great keynote speech, what we are seeing is just atmospheric model results. And you know, the atmospheric model may have so many uncertainties, including the model selection and the model parameters. And the point is a small change in your model settings will significantly change in your future state estimates. So the question we should ask is that how to distinguish the effect of initial conditions and the effect of model uncertainties. So to solve this problem, we are now proposing some kind of a new regime of the meteorological modeling. So in most cases, we assume the fixed model parameter or fixed model selection. As I will explain later, actually the model selection can also be recognized as a parameter. But anyway, we assume it is fixed. And then we try to estimate the state space, such as wind and temperature. And sometimes we're going to assimilate the sparsely distributed observation to improve the estimation of the state space. But we no longer assume that parameter is fixed. Parameter can be spatio-temporally distributed. Parameter can even change in time because your uncertainty may change in time according to the surrounding conditions. Okay, so this is a kind of new regime, and the advantage of this the viewpoint is that it is explainable compared with the deep learning method to mitigate the model uncertainty. But we can freely solve the model-related uncertainty. And I do not have much time to explain the details about the mathematical methods, but our library called HOPE ENKF includes the machine learning and data assimilation to accomplish this complicated task. And then I will explain some of the examples. So this is the parameter optimization by the geostationary satellite, because our focus is on the tropical cyclone, and the tropical cyclone we do not have much in situ observation for the tropical cyclone. So over ocean, the geostationary satellite is a very good information for the tropical cyclone monitoring. So we perform the Bayesian inference of the WRF model parameters based on the Himari 8 geostationary satellite. So by comparing the model estimated the images and the real world Himari 8 images, we're going to try to posterior distribution of the model parameter. It means that we not only optimize the parameter, but also we add some uncertainty as information. And we can successfully optimize both crowd microphysics parameters and the boundary parameter. And then we can somehow improve our intensity forecast, shown in the lower right figure. And actually, many of our colleagues often say that, okay, model parameter is always important. However, the parameterization selection is more important. So how to quantify the uncertainty in selecting the model parameterization? Our idea is that the model selection problem can be actually recognized as a parameter optimization problem using this blended model concept. So in most cases, if you are the WRF user, you're going to choose one of the parameterization scheme. But in the blended model, we call all of them. So instead of choosing one scheme, we call all potential schemes to calculate the weighted mean of the increment of the state variables. And then we optimize the weights as parameters. So if you like the equation, I hope you do. So if you like the equation, you can write something like this in the ordinary atmospheric model. We choose option 1 or option 2 or option 3. But in the blended model, we call all of them in every single atmospheric model time steps. And then we're going to optimize the weighted parameter, weights as a parameter. So in that case, the parameter optimization or Bayesian inference of the parameter optimization can be directly used for the parameter model selection problem. And then we apply this idea to the operational ensemble prediction system in Vietnam. So with the collaboration of the great scientists in the Vietnamese hydrometeorological agencies. So in Vietnam, they've already have the 32 ensemble prediction system. So this is actually the physical ensemble prediction system. So they perform the 32 combination of the physical parameterizations. So they raise 5 physics, and they have 2 schemes for each 5 schemes, and each 5 physics. So the 2 to the power of 5 equals to 32. Okay, but we replace the discretized choice of the parameter to the blended choice. And then we optimize the blended parameter using the rainfall observation. And then on the right, you can see it clearly, our ensemble rainfall prediction is much better than the operational system. And the point is that these 4 rainfall events are not included in our training set, so that our blended parameterization can be transferred to the new severe rainfall events. So although the uncertainty quantification is always important for the weather control, but it is actually also contribute to improving the weather prediction operationally. All right, so this part is solved. So let's think about the computationally efficient way to find the good the perturbation to the initial condition, because we can actually consider the model uncertainty. And our idea is to borrow some methods from the control engineering. So on the upper side shows the model predictive control. And then actually classically, we know that the model predictive control is really similar to the smoother type data simulation, such as 4D bar. So model predictive control try to insert the small input to achieve the control goal, showing the green star. So on the other hand, the smoother type data simulation, or 4D bar, try to introduce some input or increment, small increment, to realize the observation in the future, showing the green star. So they are actually quite similar. So we apply this similarity to the ensemble Kalman filter to build some new method called the ensemble Kalman control, or ENKC. So ENKC is quite simple. So we perform the ensemble Kalman filter to get the state estimation, and then we perform some extended forecast. And the duration of that extended forecast is called a control horizon. And then we evaluated your extended forecast within the control horizon. Actually, what we should do is just to assimilate your control objective as the observation. And then we add the analysis increment or control increment to your real system. So the advantage of ENKC is that it is feasible for the high degree of freedom, as the ENKF is. And also it is feasible for the quasi-linear or weakly nonlinear system, as ENKF is. And it is ENKC is easy to implement because you are quite familiar with the ENKF in the meteorological domain. And also, we can explicitly consider the uncertainty related to observation as well as model. So because they are fully ensemble systems. So what I discussed in the previous slide can be directly introduced into the ENKC. And also, we have some extensions to further improve the potential of the ENKC. On the left, in many control problem is actually written as inequalities. But we can actually deal with this kind of the inequality control objectives within the framework of ENKC. And on the right, we try to minimize the area to be perturbed, because what we can do is quite small. So we try to integrate some mechanism to enforce your perturbation local in the framework of ENKC by using the existing data assimilation idea and the control engineering idea. And this is some of the test bed or toy model. So I'm still just enjoying our mathematical method actually, but this is a Lawrence 63, a quite a famous model, and our program directors proposed this problem as a test bed for the controlling chaos. So the blue is the original attractor, but by introducing quite a small perturbation, we can constrain this trajectory into the red, showing right. And I do not have much time to explain the right figures, but basically our method is really efficient and actually more efficient than the previous methods. And this is still the toy model, but we also use this ENKC idea to the quasi geospheric global model. And then our control objective is quite simple. Try to eliminate a strong wind larger than 17 meter per second. So as I explained, we can directly add your inequalities to solve the ENKC problem. Okay, so it is quite simple, and we can efficiently eliminate the wind speed larger than 17 meter per second without altering the another part of the atmosphere. Okay, so the mathematics is ready. So let's move on to the more like a physical understanding to solve this quite a difficult problem. So the motivation is that it is absolutely necessary to understand the interaction between the macro scale phenomena and the micro scale phenomena that we can control, right? And our target is tropical cyclone. It is too big, right? But I would like to say that we are ready to understand these interactions, because this is the result of the satellite data assimilation analysis and the prediction field. So on the left shows the GOES 16 satellite observation, but on the right is a WRF simulation. It is almost identical, not only for the entire tropical cyclone structure, but also in the individual convection within the tropical cyclone. So by using these kinds of data or infrastructure, we can investigate the relationship between the smaller scale phenomena and the macro scale tropical cyclone. And this is the composite analysis of so many convective activities within the tropical cyclone from our data assimilation analysis. So we actually decomposed into the many signals into the scale. And if you look at the third figure from the left, we can see some robust signal, because this is a composite of the many convective activities. So this signal is robust. So robust moisture convergence can be found in this scale before approximately 15 minutes before the ignition of the convective activities. So the next question is, what if only this convergence is smoothed out without altering any others? And our answer is that we can actually diminish the rapid intensification of the tropical cyclone. So first, when the convergence of the moisture is smoothed out, many convections around the center of the tropical cyclone can be suppressed. Okay, so we do not directly suppress the convection. We just smooth out the smaller signal of the convective activity, but we can successfully diminish the convective activity. And then if you do not have any strong convective activities around the tropical cyclone center, although the total moisture does not change, but rapid intensification does not occur if you look at the orange line in the bottom figure, right? So this is a scale interaction between the smaller scale and the larger tropical cyclone. But of course, the human being cannot smooth out those moisture fields. So it is not realistic. But I'm now saying some theory about the interactions between the smaller scale, human being scale, and the macro scale weather phenomena. And actually, we found we are now facing some difficulties in which the even single convection cannot be suppressed in the quite a strong, super strong wind field and over ocean. So we hypothetically prepare the ship in the simulation and try to reduce the moisture in the lower atmosphere. And this figure shows that any single dot indicates the convective activities. So more than 1,000 convective activities try to be suppressed using this ship. And if the dots are located in the lower right corner, it means that your convection activities is successfully suppressed, but most of them cannot be suppressed efficiently. So still it is quite challenging, but we've already have some mathematical theory, and we've already have some physical understanding of the scale interactions. So by combining them, we are now challenging the controllability of the tropical cyclone. And lastly, we're going to about how does this possibly the new social infrastructure can really contribute to the society. And there are so many issues of including the ethical or legal or economic, so many issues. And maybe on the next day or day 2 or at the end of this day, we're going to intensively discuss about that. But I just raised one of the important issues on it. So what kinds of weather control can be feasible for social decision making? In principle, the weather control interventions or deciding that we do not intervene to the atmosphere, such kind of things should be made based on the social collective decision making by all affected by the extreme weather. But okay, let's think about some cases. For instance, to consider that the weather control can mitigate the total damage of a disaster, but somehow increases the risk in the specific region, even though that increase of the risk is not so substantial. But what we can agree in this case. So we can suppress the convective activities, but we can slightly change the location of the convective activities, for instance. Okay, so that's quite tough to answer, right? But let's think this kind of situation using a hypothetical simulation without avoiding discussing it. Okay, so this is the case study of the Hagibis, tropical cyclone Hagibis, which is a costliest tropical cyclone in Japan in the modern history. And we actually performed 1,000 ensemble impact-based forecast. So impact-based forecast means that we not only consider the rainfall or wind speed or any other meteorological variables, but also in the real disaster hazard, such as flooding or coastal storm surge. So imagine that these 1,000 members are possible future realized by weather control. Of course, it is not in the case actually, but let's imagine that you can choose 1,000 members, but can you choose? That's the question. So ask yourself, can you choose a good future for all? Okay. And to do that, actually, doing this kind of an assessment can also be the research. So we need to perform the impact-based forecasting. We should have some good hazard model, including a river and a coastal, and because we would like to perform the 1,000 ensembles so that the computational efficiency quite matters. So we try to develop super efficient but precise the river model and the coastal model, introducing some machine learning technique. And also the vulnerability strongly depends on the human activities, right? So how human make a decision to evacuate or not. So we would like to investigate such kind of point in the individual level by looking at your brain, and also in the community level by interacting with each other. Okay, so you're gonna decide to evacuate because you are a reliable guy says that, right? So that's kind of the network effect is really important to think about the human behavior. And this is not so much holistic result. This is kind of just a showcase, but the individual line is an individual scenario quantified by 1,000 ensembles. So, and then, it's quite complex. So the point is, if you would like to pick one of them, one scenario shows a strong rain, but that scenario does not have any high risk of the storm surge. But if you look at one scenario which has a strong storm surge, does not have so many floods in land or river basins. So it is super complex. So that's kind of trade-off between the hazards. So it is not so easy to determine which scenarios are best in real case, if you look at the real case uncertainty. All right, so that's a wrap up, and thank you very much.